Hi everyone, I'm going to be going over sorting and searching, so this should be our last standard template library lecture. I might add another one. I don't know how far I'm going to get here, so let's see how well we do. This is one of those standard things that every computer scientist look at, and it's one of those great illustrative examples of why you need to actually study computer science, or at least why you have to understand how to think computationally, how to think algorithmically, because the simplest solution is not always the correct solution. Now, we are not going to do, you're clearly not doing a full computer science degree, but at the same time, learning to program, it is expected of you that you are able to do at least this. Very much like you are not mathematicians if you do engineering, but you're expected to be able to do some calculus. So, sorting and searching comes up all sorts of places, and it is at least a first pass that we have for illustrating why we have to worry about complexity. And so, but first, let's actually go over a couple little things. We looked at this out of order pseudocode. I asked you to do that as an exercise last time around, and I'm sure all of you did it. Yeah. Um, anyways, we're gonna have a look at that out of order array. And in case you're wondering, hey, that's impossible. That's incredibly difficult to do. There's also going to be a video posted online very, very soon of my eight. Is he eight? I got a 2012. So whatever that is. Um, yeah, my son. He's about to be 8-year-old son doing that out of order algorithm. To a certain extent, he's doing it with a deck of cards. He's not actually doing it with code, but we can actually look at the code. Beyond that, I wanted to do one other standard template library question. So, in case you think it's too hard, no, it just might mean that you need to take a step back, think about it how you would do it as a person, and then figure out the algorithm. It's not difficult in terms of the thought process, it might be difficult to implement. I wanted to go over two other functions, and I'll actually show this live. So, to do srand and rand because it comes up in the lab. So, I have a whole bunch of code in here. Let's do I want to get a random, I want to get some random ranges here. So I want to get a random array of integers, and so I'm going to generate a random number array of size. I know, very original name. So these values that I'm going to get are normally I'm going to make them between test min num, test max num, inclusive. So it could be include this value, it might include this value, and everything in between. And the size of this random array of values is going to be size. So first of all, if I give you a value of size, it's equal to 0. I give you an empty array or null, right? Or I give you null. Okay, so first things first, let's make a brand new array. Great. And then here I am seeding my algorithm. So what the heck is that? I remember asking somebody about that as well when I first used a random algorithm or a randomization or random number generator, I should say. srand is to seed the random number generator. This is not actually a random number, a series of random numbers. That's actually extremely difficult to do. So a lot of languages, C included, and you have to take this, so you have to sort of, as long as you're not doing some safety critical system and you're trying to prevent another country from attacking our country, that sort of thing, it's okay to use this as a random number generator. But people can predict what you're actually doing with that random number generator. Because what C and all of these languages have done is they've pre-computed or they've pre-calculated a series of very long series of random numbers. It's already generated. And it's such a long list of numbers that if you start at any position within that giant array of numbers, and you start at position 4,297,000 and start there, then it effectively looks like you're generating a random bunch of numbers because they're already random, and you find some random starting point. That is what we mean by seeding a random number generator, in this case at least. To seed a random number generator suggests making this new to start off or to make this new set of random numbers. But for C, so that's why it's called a seeded random number generator. You put the seed into the ground and it starts growing, right? A seeded random number generator for C and C++ is finding the starting point somewhere in there. But effectively, you give it some number, that's where it's going to seed or start your random numbers. So I actually need a random number to put into my random number generator. I know, that sounds wonderfully obvious. Well, it turns out we do have a way of getting a random number. I can just get the time. There is a function called time. If I put in a 0, I will get the current time. It will give me the current time in milliseconds since 1972. It might be in seconds, but either case, it's effectively some number. It doesn't get me the next position in the random number generator. It gets me some random position in the random number generator where I start. So if I put in the time, called time at position 0, at time 0, it will give me the current time, and if I put that in my random number generator, it will position me somewhere randomly within the random number generator. That's what that seed rand does. If I don't do this, all my random numbers will look exactly the same each and every time. The benefit of this approach is if I want to make sure my random number generators always give me the same values, so I figure it out one time and I want to make it consistent afterwards, for example, I would need to record that time or have some value that I put in here. If I put in 100 and call for my call to srand, I will get the same random, quote unquote, random numbers each and every time. Unless this number is different, then random number generator will generate the exact same seemingly random numbers every time. So if I want seemingly random behavior but consistent time to time every time I try it, I put in some kind of number here, a normal number in here, and if I actually want it to be really seemingly random, put in the current time. That's not going to be the same current time as any other time you run your program, and therefore it's going to be looking actually random. Okay, so that starts my random number generator. And then afterwards, I am going to I need to get the range between some value and this value, and I want to get a random value in this range. So I have a function called randRange. It has the minimum value, it has the maximum value, and I need to figure out what the heck this thing does. So every single element in my array, I'm going to get a random number between this value and this value, and I'm going to put it into my return value, my array that I'm dealing with. So randRange has got to be something useful. So here we go. Let's find it. Here's what randRange does. It takes in my minimum value. It takes in my maximum value. And so my real range that I have is the max minus the min plus 1, because I want to include the maximum. That's the actual range that I have, the actual difference between the minimum and the maximum. And here's what my actual random number generator will do. Rand will always give me a value between 0 and rand max inclusive. So it will include 0 and it will include rand max. So if I want it to go below some minimum, like from -5 to 10, what do? I can essentially add -5 to it. So subtract 5. That's my minimum. And then I have some scale factor. I have some value between 0 and rand max, and then I multiply it by some scale factor, which is my real range divided by the maximum, the range that this thing is going to give me. Effectively, I want some way, and that might actually not work as well as I want it to. Hold on, let's do this. I wonder if my random number generators have been actually working correctly all this time. So that's a double. I'm going to cast it to an int afterwards. Or I could, so I have a random number multiplied by that. I'm going to do that, and then I'm going to, for all I know, I could have had something wrong with my code this entire time. So actually I want this. Oh no, that's going to be fine. Okay, so if I have this as a double, it's going to be a double divided by some integer, so it's just going to give me a double, but also if I multiply it by this rand is also going to be an integer, so integer times a double is going to be a double. So all of this is going to be a double, a multiple, and then I suddenly will cast it to be an integer. Then I'll add the minimum value. Okay, that might actually make my math work better. But the random number that I'm going to generate is somewhere between 0 and random x. The real range that I have here is whatever min is, whatever max is, so it could be larger or smaller range. And there's something missing here and there. But the rand is going to give me some value between 0 and random max, and this is me trying to get all cutesy, trying to get the math to work so that I get some value between min and max inclusive. That's all I'm doing, just a bunch of fancy cute math. This is me using the srand, which is to seed my random number generator, and rand. And this code, by the way, is on the shared drive. Okay, so how the heck? What I'm going to be looking at is sorting algorithms. I'm going to look at quicksort, binary search, chunk sort, bubble sort. I'm looking at bucket sort. I'm going to call it bucket sort, chunk sort, whatever you want to call it. There's a million one names for all of these things. In fact, I love telling the story that one of my coworkers at Northeastern, he has a sorting algorithm named that he made himself. He was able to prove it works, and he named it after his mother. Yes, so it's all sorts of wonderful. Like there are thousands upon thousands of these things. There's only a couple famous ones. So quicksort is one of the most famous ones of all, and we'll look at that quickly. That was not meant to be a pun. Okay, so we're going to look at those, and I don't think we'll have time for asymptotic growth, but we can get into some calculus if you want to. But first, let's actually talk about what we had with the out of orders arrays code. So what I was trying to do before is I wanted to figure out if an array was in order or not. So I need the size of the array, and size of the array and the array itself. What the dead giveaway if my array is out of order is if the one element ends up being smaller than the element before it. So if the previous element is larger than the next element, not equal to, less than the previous element, then I return that position that I'm looking at. Otherwise, I'm going to return -1. That's it. So here's this how it would work. So let's see if I can get my pen. If I have my pen around, I have a cat around here, so who's getting in the way? Yes, you are getting in the way, cat. Okay. No, I'm not gonna find it. So let me use the mouse temporarily, at least. Here's how the algorithm is going to work. I'm going to check. I'm going to start off with 1, go to, but not including size. So I'm going to start at this position. I'll check, is this greater than or equal to this? Or is this smaller than this? Well, sorry, is this larger than 2. Is 1.1 larger than 2.1? No, it is not. Is 3.3 larger than, is 2.1 larger than 3.3? No, it is not. Is 3.3 larger than 2.5? Yes, it is. And at this point right there, at this 2.5, I'm going to return the value. So I'm going to return the value, whatever this position here is. 0, 1, 2, 3. It's going to return the value 3 in this particular case. If my array was completely in order, I would keep on not having it ever be smaller than the previous. It's always going to be larger than or equal to the previous value, and therefore it must be in order. That is one of the aspects of what the less than sign does. It's transitive. It goes from if A is less than B and B is less than C, then A is less than C. Okay, so if I call A out of order and then whatever this array here is and the value 10, it's going to return the value 3. So let's go over searching, because searching comes up in weird, wonderful ways. It's actually one of the most common things that you do programming, and linear searches are sort of fall off a log easy. or at least most people think of them as a bit as easy, especially once you get used to them. Binary search, however, is one of the most famous algorithms we have. It's also the most infamous algorithms that we have. I love telling the story, but maybe I shouldn't tell it so often. The original binary search algorithm was published, I think, 1948. So, a long time ago, barely after the computer's invented. It was also published correctly for the first time in 1956. It was almost a full decade after the original publication when it was finally made correctly. It is one of those widowmakers. If you give it someone a binary search, write binary search, unless they've just memorized the code, which you shouldn't do, nobody writes it correctly. Everyone gets it a little bit off. Every single term, I would ask my students in a logic and computation class, I'd ask all of my students to write binary search. I get a big handful of papers at the end of the class. I check every single one of those papers. I may have had one student who wrote it correctly, and I'm pretty positive it's because they just stole it from online. It is incredibly difficult to get right. And then we have chunk search, which is easier. Now, binary search doesn't seem hard. Theoretically, it seems hard, easy. It's just the little edge cases that get you in the end. They always get people. So, but linear search, everyone can do. So, a linear search, this is a sequential search. This is the only game in town. If my array is out of order, so it's just random bunch of numbers in there or random bunch of things in there, the only way I can do this is a linear search. I got to walk down my array or down my list or linked list or whatever I'm using. I got to walk one element at a time and check. Hey, are you the one I'm looking for? Nope. Are you what I'm looking for? Nope. Are you yeah, just one at a time. That's the only thing I can do. And I just sequentially walk element by element. Okay. So here is me doing a linear search. I'm going to I'm looking for the value, let's say 2. Okay. So I check 17. Are you 2? Are you 2? Nope. Are you 2? 23. Nope. 5. Are you 2? Nope. 11. Are you 2? Nope. 2. Are you 2? Yep. Ding. I return this value and I'm good. How about if I check the value 1? Yep. Are you 1? No. Are you the number 1? No. Are you the number 1? No. 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 Crap. I walked all the way to the end of my list. If it's not in my list, I got to walk all the way to the very end, no matter what. That's the problem with a linear search. What we're talking about for a linear search, let me clean this thing if I can. I don't think I can clean that up. Okay. What we're talking about with the linear search is this line right here. Here's my linear search. No matter, so if my list is twice as big, it takes 2 times as long to do linear search. If it's 4 times as big, 4 times as long. It directly linearly grows with the number of elements I have there. There are some things, like an n-squared algorithm. This is an order n algorithm, and then I'll have some things that do the and they don't even grow. They're just like this. And then I have log base 2 of n algorithms. Anyways, a linear search algorithm, as n gets bigger, the time gets bigger. Some things are really ugly, like actually n squared is not even that ugly. N factorial is really ugly, but there are some things that will take longer. As I get more, as the number of elements that get bigger, the thing gets slower, and it gets really slow really quickly. So linear search, if I'm looking for the value 11, I need to check 17, 23, 5, and 11. If I'm looking for the value 7, I got to walk all the way to the end, and I don't find anything, and then I'm done. So I can have a while loop, I can have a for loop if I know the number of elements I'm looking for. I check to see if what I'm looking for is what I found what I'm looking for. If so, return found. Or I set off a flag saying it's found or it's true. And then at the end, I just return that position. Okay. So I normally just do a for loop. Instead of this way, I would do for int I is equal to 0, I is less than some kind of size value, I plus plus, if list I is equal to let's return the position, so let return I, and then I want to just end my for loop. If I didn't find it at all, I want to return -1, let's say. That's an easier way of doing it. Either both they're logically equivalent. So here's how the thing would actually look in code using a while loop. Fine. One of the benefits of this thing is that it's a really easy algorithm. I just wrote it with 4 lines with a for loop. Fairly easy. The arrays can be out of order, doesn't really matter. It is our workhorse. If I want to find something in a list, that's what I'm writing all the time. But it's painfully slow. It's as slow as we're going to get for a searching algorithm. You're not going to hopefully ever get slower than that. At best, if it was sorted, best case scenario, I stop about halfway on average. That's still just as long because as n gets ridiculously big, 500,000, it's still a pretty big number. So this is where this is why I don't use linear search for really big numbers. And if you gave a linear search on a Google interview, they'd sort of laugh in your face, right? So on average, even if I could stop halfway and just say, okay, I'm past, if there were an order already, I'm only going to do half the amount of work. But even if I do half the amount of work, it's still pain. So here's chunk search. Chunk search allows me to go chunk by chunk down this thing and try and find the element I'm looking for. And it only works if the array is sorted. I have to find out how big a chunk is, and so I get to decide how big my chunk is, and I check the last element in each chunk to see if it's larger than the thing I'm looking for. So if I will search for 1, what's going to happen? I'm going to check this one. I'm going to check whether 0 is less than 1. Is it less than 1? Yes, it is less than 1. I'm going to keep on going. Okay, how about 2? Is 2 less than 1? No, it's not. Okay, once I know I'm searching for 1 originally, I check for this one, I search for 1. 1 is less than 2, so okay, then now I need to do a linear search through this chunk. I know it can't be in here. They're in order. Everything before this 0 got to be 0 or less. Everything here is 2 or less, but 0 or greater, right? That's the only possible values in here. It's between 0 and 2, because this is the maximum value in this chunk. So, and this was the maximum value in this chunk. So therefore, the value has to be the value's got to be somewhere in here. So I then do a linear search. Is this it? Nope. Is this it? Yep, it is, and I would return that value. How about 4? So is it in there? Nope. How about the 2? Nope, it's still, the 4 is bigger than the 2. How about this one? Okay, now I know what the 4 is. The 4 is probably going to be in here if it's going to be in here. So let's do my linear search. Is this it? Nope. Is this it? Nope. Is this it? No, it's bigger than the number 4. Therefore, 4 must not be in here. And then I'm going to return -1. How about 12? Is this it? Nope. Is this it? Nope. So let's put these in here. 12, 12, 12. Is this it? How about this one? No, still too small. Oh, wow, I'm out of chunks. I'm done. So I keep on going, jumping chunk to chunk to chunk, looking to see if the value is larger than the thing I'm looking for. As long as that element I'm searching for is always larger than the last element in that chunk, I know I have to keep going. And as soon as I find it, the last element in that chunk is larger than what I'm looking for, I do a linear search through it. The question is, how big should that chunk be? Because what are my worst case scenarios? Let me think about this. So think about what could be the worst case scenario here. What's the worst possible chunk size that you can give me? So there's two smartass answers in this case, right? One of the smartass answers is, I got one chunk. I go to the end. Is this it? Nope. I got to search my chunk, and then I got to do a linear search all the way through my chunk, right? So I have one big monstrous chunk. I check, and then I do a linear search down there. That's one worst case scenario. So there's a couple smartass comments. What's the other worst case scenario? It's I have n chunks. That's just as bad, right? Because each one I go, is this it? No, no, no. Wait a second, that's a linear search all over again. No matter what, in both those extreme cases, I'm back to a linear search. So there should be, what I'm hoping for is about half the time it's going to be, I'm going to jump chunk to chunk, and the other half the time it's going to be linear search. I want to split it in half essentially. So if I have n elements, so what I want to do is so to claim n things. Well, what I want to do is I need to do m. So let's say how big is each chunk? If I do m steps, I want about halfway. So if each chunk is size m, and I'm doing m jumps, that's exactly halfway. So therefore, m would be the square root of n. In fact, that is the time of my algorithm. It's not much. It's way faster than just n steps, but it's still not ideal. And don't worry about that O thing. That's what's called big O. You're not going to be covering this in class. We're not. This is just sort of force of habiting, or in case you look at it, the long and short of that O means it's in the order of, it's about square root of n steps. It might be a bit more. It might be a bit worse. It doesn't matter. Square root of n. So this is what we're looking for. I want some kind of a rough approximation of how fast this thing is. This is faster than linear search. It's still not ideal. That's where we need binary search. And binary search, you can actually mathematically prove that it's as fast as you can possibly get it. There is nothing that will be faster than this thing. Just the nature of how it works. Now, you can try and optimize it in certain ways, but that's essentially what it's the best we can do. This is about the best we can do. Okay, so here is binary search. We find the center point. We say, hey, is this what we're looking for? If what we're looking for is less than this point, it has to be sorted, by the way. So if this is less than what we're looking for, well, we know it can't be in all this other stuff, right? If the thing I'm looking for is less than this value, then screw it. Get rid of that. Okay, so now I find halfway point again. How about this value? Is this less than what I'm looking for? If it's less than what I'm looking for, well, it's actually greater than what I'm looking for. Let's pretend. Okay, well, can't be in this chunk. Okay, and then I keep on splitting it in half, find the center point, is less than what I'm looking for. Okay, let's get rid of this part. And I keep on throwing away half my array at every single step. Every time I do a check, I throw away half the array. I do another check, and I throw out half the array. I normally do this demonstration with a phone book, back when they used to have phone books, or a dictionary. I love doing it because you get to throw the book across, rip it in half, and throw it across the room. It's quite fun. And it's very, very effective. So instead of, I used to do a linear search with a dictionary. Just give me a random word in the dictionary, and I go through the A's one after the other. And after about 10 or 12 words, people are like, okay, yeah, that's boring as hell. Chunk search. Let's pretend letters of the alphabet are my chunk. I jump to, let's say I'm looking for, one student gave me dinosaur. It's not A. Okay, go to the next chunk. Not B. Go to the next chunk. Not the end of C. Go to the next chunk. End of D. Oh, it must be in the D. So then I would do a linear search through D. Still takes a damn long time. Binary search is I get halfway through my dictionary, rip it in half, throw half the book across the room. Go to the halfway through that again, rip the book in half, throw it half across the room. In less than 18 steps, I'm done finding any book, any word you can give me in the dictionary, no matter what. I can do it in 18 steps. It was literally 2 to the power of 18 number of words I can sort through with a binary search and be done with it. So this is really, really small. And we'll say it's a damn small number. So if I have, let's say, 2 to the power of 18, this will require 18 steps. That's it. That's why binary search is so famous. That's why people love it, but it's also why it's a little bit dangerous. Okay, so every time I find the middle point, check to see if it's what I'm looking. You can check to see if it's what you're looking for. You don't even need to do that actually. That one extra step can actually slow you down. But for the time being, check to see if it's what you're looking for, and then stop if it's what you're looking for. Statistically, it's extremely unlikely that that's the case, and so you could actually just keep going until you only have one element left. That's another approach. Okay, so let's do binary search. And we're going to see if the value 11 is in this binary search. Okay, well, we examine 11. Is it what I'm looking for? Yes, it is. Stop. Okay, that's not so fun. But yeah, I'm looking for the middle point. How about 7? I check 11. Is it what I'm looking for? No, it is not. Okay, it is everything. It can't be 11. It also can't be any of these things. Okay, find the middle point. 3. The middle point of these 3 elements. Right? It's not in these. It's the middle point of these 3 elements. So 3. Is that what I'm looking for? No, it's not. It has to be. It's bigger. The value I'm looking for is bigger than that. I only have one element left. Check 5. If 5 is what I'm looking for or not, doesn't matter. I only have one element left, and I stop. This thing would return -1. It's not found in my array. It required for me to do 3 steps. Now, it doesn't seem like a huge impact, but it makes an incredible difference in terms of speed when it's done right. And I think in the labs, we're asking you to race binary search and linear search and see which one completes faster. It's very, very satisfying when you get that off the ground. The normal search in a binary search in the standard template libraries is a little bit quirky, and I can help you guys if you guys are having any trouble with that for the lab. If you get that off the ground, it's fantastic to see it in action. All right, there you go. There you go. Done. I shouldn't have scratched up the thing. Here's my binary search algorithm. I'll give you the actual code. It looks a bit better. So I check my first. I check my last. The last is it depends on how I want to do this. I normally include the size of the last, and last is never an actual element. Depends on how you want to do it. And I find a middle position. So what I want to do is, if I found it yet, or if the first is less than the last, then I also want to stop. Those are my stopping conditions. I get the midpoint between the first and the last, exactly halfway. I then see if what I'm looking for is in the middle. If it is what I'm looking for, then I'm going to stop. If the value is greater, if the element in my array is greater than the value I'm looking for, I'm on the first half of my list. Otherwise, I'm in the second half of my list. And all I've done is I've updated where my last is, I've updated where my first is, and so I keep on removing half my array each and every time, because I'm looking at the range between the elements between first and last, and I move first to the midpoint, or I move last to the midpoint, around the midpoint. I keep on removing half my elements every single step through that while loop. And yet every one, it's a very simple, it can be even simpler code-wise than this, and yet everyone will screw that up. Okay. The benefits of this thing is that it's way faster than anything else you're going to use. It's actually one of the great triumphs in terms of computational complexity. It's way more efficient than linear search. It's painfully faster than linear search. It only takes log 2 base 2 comparisons, but my god, it's hard to get your head around, and the array has to be sorted, which is a huge thing. That's not trivial to have a sorted array. It only works if it's sorted, which brings us to sorting. So if I need to have these things sorted, I need to have some algorithm that will actually sort things. And that's what we're doing for the next homework. So, uh, so what we're going to do with the sorted array, and I just out of paranoia, I'm going to keep this. Hold on a second. I'm going to be paranoid. All right. The paranoia was if I was not actually recording. That would have been embarrassing. Okay, so for sorting my arrays, or anything, I can sort linear, I can sort vectors, I can sort linked lists, I can sort whatever I want. Here's the idea. I would like you, well, I want you to take a step back for a second and think about how you might sort an array. So this is extremely common. It's people found out about these things, and it was like a gold rush. Everyone was making a sorting algorithm. The idea is I can take this array up here, convert it to an array like down here, where every single element, the next element, -1, is greater than or equal to -2, 1 is greater than or equal to -1, 2 is greater than or equal to 1, 3 is greater than or equal to 2, 4 is greater than or equal to 3, 4 is greater than or equal to, see, not just greater than or equal to 4, 6 is greater than or equal to 4, 8 is greater than or equal to 6, right? But that means I need to figure out how to move things around so that the 4 goes in the right place. I've done a lot of videos online, and I think it's a good idea to have a look at them. Had a couple videos with my sons doing it because how do I frame this? They're bored, they're at home, they're not allowed to go outside or do anything else. I need to get them occupied. So they got involved in doing some videos with me. I did some card videos as well. Sorting out a deck of cards is one of those great examples. So I would like you guys grab something. So let's make sure, there we go. I would like you guys to grab something, anything around your house that you can actually sort. This could be your comic collection. This could be it could be a deck of cards. This could be arrange things in terms of size. It could be your whatever, something that you can have a definitive ordering for. Something normally with a number is the best for it. But anything that you can come up with, you could be CDs in terms of if you know what a CD is, that is CDs in terms of the title of the CD, for example. It could be alphabetical, or it could be alphabetical order for your library books, or for your books on your bookshelf. Whatever floats your boat, I want you to sort that particular element. So take a pause right now. I want you to sort it, and I want you to think about how you're sorting it. I won't tell you how to do it. Just think about how you would sort those items. So I'll pause now, go off, sort something, and then we'll come back. Hopefully you've come back after having sorted something. I'm actually quite serious. Go and sort something if you didn't already do it. So everybody does it in their own kind of natural way. When I'm sorting your exams, when I'm trying to give them back, I sort it one particular way. I use insert and sort, technically. Actually, I'll use a chunk sort first, and then I might do an insertion sort later. If I'm doing my comic collection, I'll do an insertion sort. My son did a selection sort. My other one did a bucket sort. There are all sorts of different ways of sorting out values. So let's have a look at what some of you may have done. For some reason last term, a bunch of people gave me a bubble sort, which I don't find it's intuitive for writing for code. It's not intuitive for thinking about in my books. So here is an array of values. I want to figure out what, I want to put this in order. So what could I end up doing? Well, here's what I'm going to do. I'm going to take the first element. I'm going to put it in my array. I don't know where it's going to go. I'm going to take the next element. I'm going to put it in my array approximately where it's going to go. I'm going to take the next element. I'm going to put it in my array. I got to figure out where that's going to go. So I'm going to insert it in my array in the right position. It's pretty, but I'm going to put it in -2. But it would be -2, 4, and 8 by this point in time. 1, I'm going to check to see. I'm going to put it in my array. Put it in the right position. It goes between -2 and 4. 17, I find the position where it's going to be inserted. It goes right here. I may have to move that over actually. Where's my pen? There we go. I'm going to take 3. I'm going to insert it in the right place. No, no, no. It goes in between here. 3. I'm going to take a 4. Another 4. I'm going to find the right place to put it. Right in here. Let's say, put my 6. That's going to go in here. -1. Oh, crap. I'm going to go in here. -1. Going to go between -2 and 1. And then 2. No, no, no. It's going to go right in here. I now have a sorted array. What I just did, that's insertion sort. It is, I take my array, and this is normally I would get algorithms from people in the class, by the way. Insertion sort just starts putting something into the final array. I take the very first element, just put it in my new array, and every new element I pull off, I find the place where it goes in the new array and stick it in. Right? So that's normally for the comic collection. I'll have a bunch of comics, and I'll insert the comic in the right place in my array. I find it that's my more natural way of sorting things. Okay, let's give another shot. So let's figure out what we could do. Let's figure out if let's do 0 to 4, and then I'll do a 5 to 8, 9 plus. So I have some kind of buckets that I come up with based off the numbers that I have. Let's say I figure out the range of values, and I know it's going to go from -2 to 17, and so I have some kind of way of bucketing this thing. And so each one of these values, I'm just going to find out which bucket I'm going to go into. So which bucket is this going to go into? The 4 is going to go in here. The 8 is going to go in here. The -2 is going to go in here. The 1 is going to go in here. The 17 here. 3, 4, 6, -1, 2. Okay, and then from there I'm going to do a bucket sort for these things, and I'll have a -1 bucket, a -2 bucket, -1 bucket, and I'll have 2 different buckets here. This one I will have a bunch of buckets. Let's say I'll have 4 buckets here. And since my ranges are going to be between 0 and 4, I can do 0, 1. Let's say 2, 3, 4. I'm going to put my 4 and my 4 in here. I'm going to put my 2 in here, my 3 in here. I just keep on generating these different buckets I can stuff things into. This would be 2 buckets that I have. It's going to be actually it's going to make 3 buckets, 7, 8. Algorithmically, I'm going to just do it this way of 5. So there's nothing. There's a 6. There's an 8. Notice how this is really not that efficient of an algorithm. It looks very efficient when you're dealing with decks of cards. Not so great when you're talking about integers, because you don't know how big that range is. So that's a bucket sort. It's a kind of bucket sort. How about, and then we'll do a bubble sort in a second. So that's yet another sorting algorithm. Ooh, let's do a merge sort. I did it with cards, or there's a video of me doing it with cards. Let's do that here. So I'm going to take my array, I'm going to split it in half. I'm going to have 4, 8, -2, 1, 17, 3, 4, 6, -1, 2. I split it in half. I'm going to split it in half again. And so let's do 4, 8, -2. This 1, 17. This is 3, 4, 6. This is -1, 2. I'm not really doing anything at all other than I'm trying to split my arrays in half each and every time. So it's going to be 4, 8, -2, 1, 17. This is 3, 3, 4, and this is a 6. -1, 2. All right, and then I'll get 4, 8. -2, 1, 17, 3, 4, 6, -1, 2. These are all separate buckets. They're all separate things. They're all individual elements in between each. And then the question is, what the hell did I get from that? That seems like a complete waste of my time. That seems ridiculous. Well, let's actually then re-merge these buckets. So I'll take the 4 and the 8, I'll merge them together, I'll get 4, 8. And then there's a -2. I'll take the 1 and the 17, I'll merge them, 1, 17. I'll take the 3 and the 4, I'll merge them, 3, 4. They have to be in order, 6. And then this -1, 2. All right. Next, I'm going to check to see which element comes first in each of these buckets. So the 4 or the -2. And then I will zipper these things up a little bit. So what I'll do is I'll put the, so I'm going to merge these two arrays, the 4, 8, and the 2, the -2, and by just taking the first element of each of these arrays and figuring out which one comes first. Then I'll check the next one, then I'll check the next one. So that'll give, and then I'll just put that in. So -2, 4, 8, 1, 17. Let's also do that one merged. Okay, so which comes first, -2 or 1? Oh, -2. Cross that off. Which comes first, 1 or 4? 1. Cross that off. Which comes first, 4 or 17? 4. What comes first, 4 or 8 or 17? 8. Okay, well, I'm done with this one. I can just put all the rest of my elements in here. 17. I've now remerged all my things, all my elements. And the benefit is, because each of these, when I'm doing my merging, both little lists are sorted, they're already in order. When I merge them, I only have to check the first element of each one. I don't go any further. I just compare the first element. I have a pointer to the front of each of these arrays, and every time I find one to put in, I just, I move the pointer over by one position. Instead of looking at -2, I now look at 4. Instead of looking at 4, I now look at 8. That's merge sort. Oh, I did one. So I would love doing this for movie time. You can look it up yourself rather than typing in a URL. You're looking for Sorting Out Sorting. This is by the University of Toronto. It's from 1981. It's old as the hills. Now, you do not have to watch that video in full, especially with the sound on. The music is really annoying. But I want you to have a look at some of the racing conditions. And so there's some videos of their racing quick sort and selection sort and bucket sort and radix or whatever the case is. They're racing a bunch of different sorting algorithms. And you can see the time it takes and the amount of memory these things take. And it's quite alarming. What's more alarming is this is in 1981 when a couple thousand elements was a big deal. Now imagine, given the fact that the amount of data we have to deal with doubles every 18 months approximately. It's actually would be even more pronounced now than it was back then. You can put, a gigabyte and a gigabyte of array of size that's 1 gigabyte in size, and sort that thing, and it'll be an even more pronounced difference between quicksort and bubble sort, for example. It's to the point at the end of the video, and I love showing the end of the video just because it's funny as hell. They give up. They race all of these different algorithms. You could just skip to the end of the video and have a look at some of these things. They're sorting all these things, and they will give up on waiting for bubble sort and a couple of the other sorting algorithms and just start rolling the credits because it's so damn long to do. They don't even finish those algorithms before they cut off the video. It's just that much of a difference. Quicksort's long since done, like minutes beforehand, and yet bubble sort's still going, and it's not anywhere close to being finished. That's the difference. That's why we do this sort of thing, because it does make a huge difference in how fast an algorithm, how fast your code will actually run. It makes a huge difference in what you can actually handle in terms of data. This is why you have technical interviews. So have a quick look at this. I find it fascinating as in terms of complexity, and it is something that is very important. So we're going to look. Normally I'd have this little group embarrassment project where we take our sorting algorithm, and I'd have you sort yourselves. So you should feel thrilled about the fact that you're home right now, because it always is a little bit embarrassing with that one. We can sort by any number of things. We can do it in descending order, ascending order, alphabetical order, whatever you want. But it's still sorting. I just need to know, is some value A less than B? In fact, that's the criteria for these templated sorting algorithms in the standard template library. Is any data structure or any object that you give me has to be able to check the less, it has to override the less than operator. If it doesn't, it won't work. That's actually something that we had to actually you have to implement for every class or any kind of class that you have that you want to try and sort. Any other template, so that's how templated classes work. You need to adhere to certain standards in order for you to allow you to use that as a templated class. That's the standard for anything that's sorting. I need to be able to check to see if one thing is less than the other. That's it, but that's important. So yes, and I had you sort your own stuff. That was my activity for this one. So I love the fact that no matter what algorithm you eventually came up with, we've done it before. Somebody's done it before. People have spent way too much time coming up with sorting algorithms. Almost invariably, somebody's actually done your sorting algorithm as a sorting algorithm, or your sorting algorithm is wrong. Probably that it's right and somebody's done it before. So like insertion sort, selection sort, binary merge sort, quick sort. There's a ton of these darn things. If you gave me BOGO sort, that would be very impressive. BOGO sort, if you don't know, that is you randomize your array and see if it's sorted. And if it's not sorted, randomize it again and see if it's sorted. And then randomize it again. And you keep doing it until by random chance it's sorted. So it's a non-deterministic way of sorting your algorithm, and it could take days or it could take 2 seconds. You have no idea, because you're just randomly ordering your things, and just, is that it? No. Much like I don't know if anyone's watched the movie UHF. There's a scene where a guy going, is this it? Nope. Is this it? Nope. And it turns out it's a blind person doing a Rubik's cube, showing it to somebody else and saying, is this it? And the guy goes, no, and he turns it, is this it? Am I done the Rubik's cube? No. It's very similar to that. You have no idea if you're going to ever be finished. So we're going to look at bubble sort, selection sort, and quick sort, and we have some other videos as well. So have a look at the other videos. My sons are my boys are adorable. So you get to see the monkey Xavier in the video as well. The stuffed monkey Xavier in the video as well. Okay, so let's do bubble sort. Bubble sort is the classic algorithm. It's the laughing stock. It's the punchline of algorithms of computer science jokes. It's a punchline to computer science jokes, to the point that Barack Obama, before he became president, he went to Google, did a little meet and greet at Google, or TGI Friday at Google, and which, by the way, is held on Thursdays. Just, it's a weird thing. Anyways, he did TGIF at Google, and they're interviewing him, and he must have being given the answer. It's like, so what sorting algorithm would you use? We wouldn't use bubble sort, but bum. Yeah, so it's a joke amongst computer scientists, but it's still very, very easy to write. So it's out of order. The idea is this: I check a pair of numbers, and I see. So take the first and the second number. I see if they're in the right order. If they're not in the right order, I flip them around, keep going, and move up to the next one. So so every single time I'll start off with 0 and 1, and then I'll look at pair 1 and 2, 1 and so 1 and 2, 2 and 3, 3 and 4, 4 and 5, like pair by pair, walking up my array. And if they're out of order, I flip it. That doesn't mean it's in order after that one time. In fact, it just means that the absolute biggest number is at the very top. That's the only thing you can guarantee. It bubbles up the largest value. It bubbles up to the top. Only one value is guaranteed to bubble up all the way to the top. Other ones might move a bit, but one is guaranteed to bubble up all the way to the top. And then you repeat. And you keep doing this until your array is sorted. There's nothing that stops this thing. There's no upper limit to how long you do this. You just keep on doing this, walk down the array, checking to see if you flip things around until the array is sorted, and then you stop. Okay, so let's do an example. So here are my array. Here's my array. I'm going to check to see if 17 and 23 are in order. They are. No exchange. Great. 23 and 5, they're not in order. I got to switch them. I switch them up. So I get 17, 5, 23, and 11. I check 23 and 11 now. Are they in order? No, they're not. I switch them around. Notice that the very last value at the end is always my largest value. I'm not done. That 17 is still out of order. That's first pass. Second pass, check 17 and 5. Are they in order? Nope. Switch them. 17 and 11. Are they in order? Nope. Switch them. 17 and 23. Are they in order? Yes, they are. No exchange. And then I do another pass. If I have any changes that were made, I do yet another pass. Is 17 and 11 in order? Yes. 11 and 17? Yes. 17 and 23? Yes. Done. So I have a flag every time I have to do a switch. I set the flag to I got to keep going, and then I'm done. So I have a swap flag, as in, did I do this so far? Did I do any kind of swap? All right. So I have this temporary variable, so I can keep track of swapping two values around. I have a do while loop, so I'm going to keep on going while there's a swap. I just keep on doing this. I start off with there's no swaps. Then I walk element by element down my array. So I go from 0 to size minus 1. So I don't go to the very end. I go almost the second last element. And I check to see if this value here, count, position count, is greater than count plus 1. If that's the case, I got to flip them around. This should be smaller than this. Smaller than or equal to this. So if I have to swap them, I swap them around. I use a temporary variable. I swap them around. And then I set the swap flag to true. Yep, I've made a swap. You have to do this all over again. Finish this loop. Oh, is this? And then I check to see, hey, did I have a swap? Yes, I do. I got to loop around again. I do potentially swap values. If I do any swaps, I got to loop around again. And I do that when you actually do the analysis of this thing. There is a worst case scenario. Let's say what's the worst case scenario for this one? 17, 11, 10, 9, 8, let's say. What's this going to do? It's going to require n squared things. I'll do one of them will bring the 17 up here, the next one will bring the 11 up here, then the 10, then the 9, but I'm going to do approximately n squared number of calculations, right? Every single time this will swap n times, n minus 1 times. Minus 1 swaps, and then the next one will be n minus 2 swaps, and then n minus 3 swaps, and n minus 4 swaps, because it's in reverse order. And I'll do that n times, approximately. Well, if I do n minus 1 swaps, n minus 2 swaps, n minus 3 swaps, that's approximately, and do that n times, that's approximately n squared. Where n is the size of my array, just to be very clear. The size of my array is 2000. This is 2000 squared number of swaps if it's in reverse order. So, here's bubble sort, here's the trade-offs. Okay, it is easy to understand and implement. The code is fairly straightforward, but my God, it's slow as hell. For really large arrays, this thing is going to be doing a lot of things. I didn't even notice I had that particular algorithm. Hey, there you go. Look at it go. Woo! Maybe you can actually just use the video. These slides are online. Have a look at these. It has to do another swap around here. There you go. It's going to be a while. Oh my god, I'm bored watching this thing go. Oh, so slow at doing calculations. Swap it around. Then the 7 and the 4 will swap. Oh my god, get there faster. Okay. Um, Selection sort. I'm not going to wait for that damn algorithm. Selection sort. This is what I would do. One of the sort of natural things I might do. I'll find the smallest value of this. If I'm looking for smallest value, I'll find the smallest value in my array, pull it out. Find the next smallest value in my array, pull it out. Find the third smallest value in my array, pull it out. Just keep on removing the smallest value each and every time, and keep looking for the smallest value. So here's 17, 11, 2, 9, 23. That'll do. Okay. Hopefully I don't have I might have another slide on this, but I'm just improvising here. I'm going to take the smallest value. I'm going to remove it. Notice removing things from an array, slow as hell with an array. Linked list, that would have been perfectly fine. I find the smallest value, I can remove it, but I still need to walk down my entire array, find the smallest value. So I have to do n comparisons, and then I'm going to do n minus 1 compares, n minus 2, n minus 3, and so I have n steps, n times, or let's say n times. I'm still back at n squared. It's still an n squared algorithm. So I find the smallest value, remove it. Find the next smallest value. Oh, that's this 9. Remove it. Find the next smallest value. Remove it. Find the next smallest value. Remove it. Find the next smallest value. Remove it. Done. It's a very intuitive thing as well. It seems like you're going to be doing fewer exchanges. It's still an n squared algorithm. I'm not just doing as many data exchanges per se. I'm just finding values. But the number of comparisons I have to do is n squared. I don't have to move the data around. I just have to find the value, plop it in the new array. So I'm not swapping data as much, but I'm still doing a lot of work here. Until I just find the next smallest element, remove it, and keep going. So if it's so my array contains this, find the smallest element is 2, and I plop it in the front. And or if I want to do it in place, I can swap it with whatever was in this position. So what I'm doing here is swapping these two around. Okay, then I'm going to start at position 1 and find the smallest element. Oh, and then the smallest element's over here. Do I have it here? Okay, and then I swap it around. So I'm going to swap these two around. Next element, I'm going to start at the 29. Find the smallest element. It's 11. Swap those things around. And then finally, I'm at the 29. Is there anything in there? No, I'm done. So here's selection sort. I have 2 for loops. Right? This for loop here finds the minimum value, or I can have a function called find min or something like that. And I just remove I swap the minimum value with the other value, and I'm good to go. And I have a min val, which is a scratch value in here. So we'll just leave it at that, running it here. So it's more efficient than bubble sort in the fact I don't have to do as many exchanges, but I still have to do the same number of comparisons. I still have to, it's a for loop in a for loop. It's going to take n squared steps. Notice the animation is going faster than the other one. It's still slow. It's faster than bubble sort, but not by much. So quick sort, again, we haven't really done it, but I did it before with my other class. So let's actually change up my values here. Here's what quicksort's going to do. I've done it in the other video, that's why again. I'm going to find a pivot point. I'm going to find some place where I can split my array in half, or it doesn't even need to be split in half. I'm just going to find a pivot point. Now, traditionally or by convention, I want to make that as easy as possible. So I'm just going to pull since I don't know what the best pivot point is, I'm going to just choose the first value. I could have chosen the last value. I could have chosen some value in the middle. I don't care. But the easiest thing to do is just choose the first value. So I take the first value, plop it down. That's my pivot point. It's going to be where it's permanently going to go. It's not going to move around at all. Then I'm going to move around. I'm going to take every value and say, is this less than, equal to, or greater than 70, my pivot? Oh, it's less than. Put it on the left-hand side. Less than. Put it on the left-hand side. 0. Put it on the left-hand side. 99. Put it on the right-hand side. 98. Put it on the right-hand side. 44. Put it on the left-hand side. Okay. Now that I've had this pivot point, I'm going to choose my pivot point of 25 is going to be my next pivot point. I'm going to plop it down. I'm going to see, is 15 less than 25? Yes, it's going to go over here. 0, going to go over here. The 44 is going to go on this side. Okay. The 70 doesn't need to move. The 99 and the 98, I'm going to choose my 99, plop it down, and then say, hey, where does this go? 98. As soon as I have only one element in here, if I have these buckets with only one element, I know I'm done. It's in the right place. Every single time I have if I have more than one element in this on one of these buckets, I know I have to do a quicksort algorithm. Here's my last quicksort algorithm. I'll take the first element. It's 15. Plop it down in its locked position. 0. Oh, it's less than 15. Put it on the left-hand side. And I'm done. If it only really works if my pivot points are about halfway. In the video with me doing this with cards, you'll see the problem with quicksort. If I'm very unlucky, it could be if I'm very unlucky and my pivot point happens to be 0, what happens? If the pivot point ends up being 0, everything is on the right hand side of 0, and now I have to sort, and now I'm doing quicksort on n minus 1. I'm not on half the list, on n minus 1 of my elements. It's suddenly just as slow as anything else. I'm not splitting my list in half each time and doing this really cool divide and conquer algorithm. So where I do half the list, and then in each of those half, I can just do the same problem again, just with half the number of values. That's why it's called divide and conquer. If I'm really unlucky and I choose a bad pivot point like 0 or like 99, it means most elements are on one side but not the other, and now I'm doing the same amount of work. I have n minus 1 elements to do the quicksort algorithm on next. That is really suddenly inefficient. So in fact, the worst case scenario for quicksort is a sorted list. I love pointing that out. I always found it fascinating as when I was a student. The worst thing you could have for quicksort is a sorted list. So if you call quicksort and I call quicksort a second time, it's actually slower than if I had just a random, if the list was random, which is actually one of the solutions for quicksort. One of the ways that people can work around quicksort being so slow with a sorted list, honest to God, they'll randomize the list before they call quicksort. You give it any list, they'll randomize the list, then they call quicksort. And the statistical chances of it being a sorted list are so small, it's actually faster to do that than call quicksort on an already sorted list. Just how the math works. So I find that fascinating. We've already done bucket sort a little bit. So the idea is if I have a limited number of options, it's really useful, especially if I know where those buckets are, like taking your last names and letters of the alphabet and saying, okay, A to D is in this bucket, E to H is in this bucket, right? Just I can choose some bucket. Computationally choosing those buckets, not quite as nice, but the idea is I split my I take my thing, I figure out what my range is, ideally, make a bunch of buckets that approximately evenly distribute those numbers or those values, and then I put values in those buckets. Then I call bucket sort on each of those buckets. So I have my range, make a bunch of buckets, then I call quick sort on the buckets. If I have a bucket of 0 or 1 elements, then I can leave it alone. I know it's in the right order. And so at the end, I have all these buckets, all these little mini buckets, and I can just put them together in a line. No one uses bucket sort that often in reality. So if you want to go do a deep dive in sorting algorithms, sortingalgorithms.com is a great resource. More sorting algorithms than you could possibly ever want in your life. So, what you really should know, I would suggest playing with a couple sorting algorithms, especially ones that are on the homework. Those are fair game on an exam. So if I say do bubble sort, do bubble sort. Make sure you can do bubble sort. Make sure you understand bubble sort. If I say do quick sort, make sure you can do quick sort, or at least trace through it and know how the algorithm works. Maybe it's just here's a bunch of values. How would bubble quick sort work with those values? Not the actual code, but just playing with the numbers. Make sure you understand how you can sort things and that it actually works and what it means to be sorted. And figure out at least I won't ask you to code up binary search because I can't code up binary search without making an error somewhere. Almost no one can. There's always little tiny errors everywhere. Anyways, I won't ask you to regurgitate binary search, but I might ask, how would binary search work with these numbers? Like what we did with the examples here. So play around with a couple of these algorithms, make sure you feel comfortable with them. Okay, with that, I'm going to stop. I might make another mini video showing quicksort in action, especially when we get closer to assignment 6, because that's what's in assignment 6, and we'll look at that in a bit more detail. All right, thanks everyone. Have a great night, and thanks for listening.